Other applications of flexural bearings in systems are, for example, this device. No, this is not a candle holder. There's 8, which is actually the average of 7 and 9, which has other implications. But that's okay. They're fun. What is this thing for? Look how that guy wiggles, and the little ones wiggle on top. So the little ones wiggle, wiggle, and then wiggle. What does this do? Think windshield wipers. The windshield wipers in your car, there's an arm, whoosh, 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 whoosh. But I'm applying force at one point, and I've got to get an even distribution of force across the wiper blade all along the window. How do I do that? If I take 1 and break it up into 2, and then I take 2 and break it up into 4, and I break 4 and break it up into 8, and that's what this principle is. And what this device was actually for was having little grippers were attached on here, with little suction cups, so you could pick up 8 semiconductor devices at once from a tray, such as something like this, bring them over to a test head, and then by pushing down through one point, get one force applied gives me 8 even forces applied to each semiconductor test device, such that each device will have the same amount of force pushing it into its test contactor, and having the same amount of force on each device as you electrically contact them. Very important to have uniform electrical test, because you want to have the same electrical resistance between the device being tested, or device under test, which is often called a DUT, and the circuitry. And that's a function of how much force is on the electrical contact. So that was a very useful part of a tool for picking a whole bunch of devices up, going over, then boom, pushing down by applying force at one point and knowing you would have even force on all 8 devices. Another interesting use of flexural bearings was this was a tray used to hold semiconductor devices, package devices, and you see these L-shaped arms allowed the little nest to have 6 degrees of freedom, up and down. It could then move side to side. It could roll, pitch. You could get 6 degrees of freedom for the device to float, which enabled it to be, then if the device was a whole tray of these devices taken and shoved into an array of electrical contacts, you could have each device float and become aligned with each of the electrical contacts for testing. In other words, flexural bearings are not just a bearing. You can actually integrate them into forming the structure of a device itself to achieve very, very small, precisely guided motions. Again, beware. Sounds like a really great idea. It can be, but you have to be aware of your parasitic motions. And a flexural bearing also stores energy. So if you move it, well, that one broke. But if you move it and then let go, it can twang and start resonating, and it can ding, flick your device off too if you're not careful on how you hold things. So again, flexural bearings, the bearing is actually typically part of the structure. Rolling element linear bearings, modular bearings usually are not part of the structure. They can be designed into it if you want. And therein lies the key. All these bearings, you'd never generalize because you'll always be wrong. There are guidelines. There are catalogs of modular elements. You have your engineering science that allows you to design your own bearing if needed. Everything has a niche and a place. The key is to really understanding the mechanics of how they work. Write your spreadsheet, to predict what's going to happen, and that's the soul of good engineering.